Hi everybody. For this lecture, I'm just going to be running some examples. So I'll do example proofs of actually three different statements. The first one I'm going to look at is what's usually called the transitivity of the divisibility operator. If it's been a while, you may not remember the transitive property. The transitive property of divisibility means, of course, we're talking about that vertical bar operation. And that is a hard word to spell. Divisibility. That's crazy. It's got 5 eyes in it. Anyway, I'm thinking middle school, you would have learned this rule of transitivity, that if A is equal to B and B is equal to C, then A must be equal to C. Right? If that. So this is just applying the same concept, but with the divisibility symbol inserted where the equal signs are. So it would become this. The theorem we're going to actually prove, and it's quantified over all integers, for all A, B, and C in the integers. A divides B and B divides C. That's going to imply that A divides C. Okay. So let me get started on the proof of that. Oh, wait a minute. Maybe before I try to prove it, we ought to check around and make sure that it's true, because it would be kind of, foolish to try to prove something that wasn't true. Can you think of examples of 3 numbers where the first one divides the second and the second divides the third? This is not part of the proof, so I just erased the word proof here. This is just I wanted to say this is us on scrap work. Think of this as scrap paper. Please don't turn in anything to me with examples written on it. That's just not okay for proofs. How about, like, I don't know, 3 divides 18? Is that right? Should be. And 18 divides 36. That's the double of 18. But does 3 divide 36? Well, it does. So it worked out for that example, but maybe that was a weak example. I don't know. I picked something that, well, here's what happened. 3 is a prime number, and 3 is one of the primes that goes into 18. And if 18 goes into 36, then that 3 that's there hiding there in the 18 is actually in there in the 36. In fact, there's an extra 3 in the 36. But you want to try something else? How about like 5 divides 15? And 15 divides, I almost said 100, but 100 wouldn't do. 105 would, though. You can check 90 is just below 100, and 90 is, well, a multiple of 15, and so add 15 more to that. What multiple of 15 is 105? 9 is 6, I think that's 7 times 15. 70 plus 35, yep. 7 times 15 is 105. All right, so, and 5 times 3 gets us to 15. We don't have all that numerical coincidences in there. Oh, but darn it, the conclusion is really valid here. 5 divides into 105. Of course it does. Any number that ends in 5 or 0 is divisible by 5. So, yeah, we've got the conclusion again. So, I'm not totally convinced by 2 examples, but it seemed like the thing is actually true. So let's go ahead and try to prove it. There's the end of our scrap work. Here we're going to begin the proof. I'll have to write the proof down low on the board, at least starting out, but We'll erase and move to the top after this first line. So what's the first line of a proof about this thing going to be? Well, it's a direct proof we're after, and the first line is always something we can write down. It's suppose A, B, and C are, what's the phrase? Particular but arbitrarily chosen. Particular but arbitrarily chosen, or you can just say but arbitrary integers such that. Well, what comes after the word such that? We had a universal conditional sentence there. It said we're trying to prove an if then, and the if part was A divides B and B divides C. So that's the part that you get to write down after the word such that A divides B and B divides C. Right, so there's your first sentence. That's always kind of something you can fill in, almost like one of those legal documents where you get to just download it from online and fill it out for your own purposes. Well, where do we go from there? Definitions. We're going to use the definition of divisibility in two different places to develop some statements that we can work better with. So that second sentence almost always begins with the word since, and then kind of recaps the things that we just wrote down as the, what do they call it, the antecedent of the universal conditional sentence. So since A divides B, we do with them one at a time. Since A divides B, there is an integer k such that, and what's going to be the such that there? A divides B has A the smaller number and B the larger number. I feel like that looks funky. Let me try that again. A divides B means A is the little guy, B is the big guy, and so B should be the multiple of A. That is, B would be equal to A times this K that we just said exists. A times K. And we're going to have a very similar sentence written down for B divides C. So a shortcut you can do is to use the word similarly. There is an integer now. Just remember the definition of divisibility. I think it used the letter K in the definition. That doesn't mean we got to use K every time. And in particular, right now, we're about to say there's this integer that we know exists because B goes into C. And that's not going to be the same one that we know exists because A divides into B. So yeah, we've got to choose another letter for our integer. I don't like L, so let me skip over to M. There is an integer M such that that's going to mean such that a big one, C, is a multiple of B, and M is the multiplier. So just to recap, we've got B equals A times K, and C equals M times B. Let me just make a parenthetical remark, or this is not part of the proof, but think about where we're heading. We want to finally get to the thing that says A divides into C, right? And so we want C to equal something times A. So now you got to just kind of stare at the things we know, B equals A times K, and C equals M times B, and figure out how can you rearrange them so that it ends up looking like C equals something times A. Okay, I'm getting rid of that green. But now, I hope you're seeing it, I think I'm seeing it. What we want to do is have something that starts with a C and an equal sign and ends up having A in it. And basically what you can do is replace this B here with this AK, which is what B is equal to, right? I'm just drawing those lines in there so that you'll see the pieces that we're going to use here, but that's really not part of a formal proof either. So we'll get rid of that junk. All right. So how do we go? Well, we'll say thus. And what we're using there is an algebraic substitution. So you can say thus by substitution. C is equal to M times AK, which, what did I want to write it as? I wanted it to be a multiple times A, so that's easy. Just reassociate and write it as MK. So we had to reassociate and commute, but that's okay because those are laws that we're allowed to do. MK times A. Now that last, these manipulations I just did, that's just basic rules of algebra. So at this stage in our lives, I don't think we need to put in a justification for such a simple piece of algebra. All right, so that's great because MK is an integer, isn't it? You want to justify that? I think we probably should. MK is an integer because of the closure axioms. Because it is the product of two integers. So what does that mean? Well, the thing that I just erased that was at the bottom of the board tells us that now A divides C. That was the very definition of A dividing into C. So we're good. And then you can write your QED or your box at the end of your proof. Cool. All right, so the second proof I'm going to do today is one that involves essentially using the mod operation to give us a limited number of cases to explore. So we're going to combine looking at the modulo operation and proof by cases. So here's the statement. It's kind of a neat one. For all x in the integers, if you square x and look at that result mod 4, there's only two possibilities. X squared mod 4 is equal to 0, or x squared mod 4 is equal to 1. That's pretty cool. So, you know, it's kind of a strange thing that if you've got square numbers, certain mods can't happen. You can't have a value that's 2 mod 4 or 3 mod 4, only 0 and 1. In a way, this is a little bit analogous to the situation with real numbers. If you square a real number, it's always positive. So you kind of think of like half the real numbers are squares and the other half are not. Negative numbers aren't squares unless you move to the complex world. So in mod 4, 0 and 1 are squares, but 2 and 3 are not. All right, so I should have written theorem up here. Relabeling things correctly. This is the theorem we're trying to prove. Should I jump to the proof, or do you want to see an example or two to think about it? How about I sneak in a few examples over on the edge of the board here, and we'll do it in green. x and x squared. We'll just look at them and then think about what is x squared mod 4. How about I do 0, 1, 2, that's 3, how about that? So the squares are 0, 1, 4, and 9. What are the values of these numbers mod 4? Well, okay, so 0 mod 4 is 0, and 1 mod 4 is 1, and 4 mod 4, oh, that's 0. What about 9 mod 4? 9 is 1 bigger than 8, and 8 is a multiple of 4, so you see this little pattern, 0, 1, 0, 1? That maybe is a hint as to how we could do the proof. Okay, so anyway, the examples that I did so far, at least, are leading me into thinking that this indeed is a true statement. And in fact, it actually is a true statement, so let's go forward with the proof. If you're given a statement that has mod 4 in it, a very natural way to proceed is to just jump into a cases proof where you use the possibilities mod 4. So what are they? There are 4 possibilities for x mod 4. Sorry, sort of to jump the gun a little bit there. I should start with suppose x is a particular but arbitrary integer. There are 4 possibilities for x mod 4. So I'm going to talk about these as cases. And when you're doing a proof by cases, it's generally considered good form to kind of spell out to your reader what the cases are in advance. So we'll say there are 4 cases to consider. X is, well, okay, there's 2 ways I could write this. I could say x mod 4 equals 0. Let me finish out the sentence with that version of things. X mod 4 equals 0, x mod 4 equals 1, x mod 4 equals 2, and the last case is x mod 4 equals 3. I was talking just off the cuff there, and I was thinking about another way to express this, but I think we'll skip that and just talk about the modular version of this proof. Okay, so what we're going to do next is simply do a direct proof of the thing we're after in each one of these 4 cases. Okay, so our case 1, and just to remind the reader that this is x is equal to, or x mod 4, excuse me, x mod 4 is equal to 0. All right, so how do we go? Well, since x is 0 mod 4, you can say x is of the form, and this form comes out of it comes directly out of the quotient remainder theorem. X is of the form 4 times q. Plus 0 if you want, but it's kind of silly to say that, right? Where q would be the value of x div 4, and the 0 that we're getting is the value of x mod 4. Oh, I better mention that that's for an integer q. For some q in z. Man, that just barely fit. Okay. So I'll erase this and go back to the top of the board for the next case, which is going to be, we just took the 0. Oh, wait, I can't quite do that because I still have to get to our conclusion. I want to make sure that we get that either x squared is 0 mod 4 or 1 mod 4. But I'm still going to go to the erase and go to the top of the board. Here we go. Right, so the top of the board needs to argue from that last line we had down there that x is of the form 4q. And what we're trying to do is prove that x squared looks a certain way. So just figure out what x squared is then. Well, you want to square 4q, you'll get 16q squared. And just taking that one step farther, that's 4 times 4q squared. Great, so what does that say? I look like a multiple of 4. This x squared is 4 times something, and is there a remainder? No. Alright, so since 4q squared is an integer, if you want, you could throw in the little justification that it's the closure axioms for the integers, but I think we've done enough of those that we're clear on that. This is the product of 3 integers, q and a 4. So since 4q squared is in Z, by the quotient remainder theorem, you see that the quotient remainder theorem is already satisfied with x squared equals 4q squared, 4 times 4q squared plus 0. Now, I'm done for this case because there were 2 options for x squared. It could either be 0 or 1, and in this case it's 0. What's case 2 look like? This is when x mod 4 is 1. And maybe I'll cite the quotient remainder theorem right now, but we're doing in all of these is using the quotient remainder theorem, which is to say that x is going to look like some multiple of 4 plus a 1, because the remainder is 1. So by the quotient remainder theorem, I think I'm going to abbreviate quo rem. That's fine to do. I mean, that's fine to do for you guys. I'd be fine with reading that abbreviation. By the quotient remainder theorem, x is equal to 4q plus 1 for some q in the integers. Right, the saying x mod 4 is equal to 1 is saying that the r in the quotient remainder theorem is 1, and this is how it's going to look then. 4 times a quotient plus a 1. Yeah. Great, so just like before, we're going to look at x squared. Well, what is 4q plus 1 squared? FOIL rule away. 4q times 4q is 16q squared. And your outer times outer and inner times inner terms are going to both be 4q, so there's a total of 8q there. And last times last is 1 times 1. Okay. Now, is this going to be something that's 1 mod 4 or 0 mod 4? It's certainly not going to be 0 mod 4 because these things are already multiples of 4 and there's a plus 1 on the end there. Can we extract a 4 out of both of these? Well, actually, that's what I just said. So let's do it. Let's just do the algebra. This is 4 times something. What would the something be? 4q squared in the first term and 2q in the second term. And then there's a plus 1. And maybe I can just jump to the chase there and say, thus x squared is 1 mod 4. x squared mod 4 is equal to 1. Well, we're halfway there. What's case 3 going to look like? What's case 4 going to look like? Honestly, really similar to the ones we've just done, but a notch more complicated. Yeah, so case 3, we're on to case 3. And this is where, which ones have we handled so far? X is 0 mod 4 or 1 mod 4. So here, this will be x mod 4 is 2. Right. Again, by the quotient remainder theorem, what form, what shape does x have? X is equal to 4 times q plus 2. All right. Let's work out what x squared is then. First of all, you can just say it's got to be the square of the thing I just wrote down. It's 4q plus 2 squared. This gets a little tougher because the numbers are larger involved in FOIL ruling that out. But what does it come out to be? 4q times 4q is still 16q squared. The outer times outer and inner times inner terms are both 8q there, so we get another, since there's 2 of them, we get another 16 times something, 16q. And last times last is 2 times 2, which is 4. Do you see that that's all, everything in here is divisible by 4? So this is 4 times an integer. 4q squared plus 4q plus 1. So since 4q squared plus 4q plus 1 is an integer, again, the quotient remainder theorem tells us that x squared here is 0 mod 4. It's literally a multiple of 4. Guess there's room to get started on case 4 because this is a good outcome too, right? We're hoping to show that x squared is either 0 or 1. And our cases so far have done 0 and then 1 and then now 0. So I bet the last case gives us 1. Here we're dealing with the scenario where x mod 4 is how much? We were going up sequentially, so we were at 2. This next one is x mod 4 is 3. Okay, so again, by the quotient remainder theorem, we get to say something about what shape x has. X is equal to, oops, that parenthesis got crazy out of hand. X is equal to a multiple of 4 plus 2, right? Because 2, am I in the wrong place? I think I'm in the wrong place. X is 3. Yeah, 4q plus 3. Just the mod notation means what's the remainder. So we're going to have 3, and the other part we're going to multiply by the divisor 4 that we're dealing with. For some q and z. For some integer q. Well, I guess there's room to squeeze a little bit more in at the bottom of my board here. The next thing is, like in all the previous cases, we're going to now look at x squared. So then x squared is, well, it's 4q plus 3 squared. And this is the hairiest of the FOIL rule things we're going to have to work out. I'll erase first and then we'll see it. All right, so what do we have? We were at 4q plus 3 squared, and that is going to be 4q times 4q is 16q squared. You know, these things all started with 16q squared because the first term in the binomials we were expanding were all 4q's. Wait, it was 4q plus 3, right? Just want to think about this. So outer times outer is going to give us 12q, and inner times inner is going to give us another 12q. Excuse me. So that 12 and 12, that's 24q. And what else do we have? That's 24q plus, the last times last is going to be 3 times 3, or 9. Oh, well, you see this is a multiple of 4, and that's a multiple of 4, so both of these together are a multiple of 4, the remainder is 9, right? No. So watch out for that. Is 9 the right size to be a remainder? It's not. A remainder's got to be somewhere between 0 and 3. Can't even be 4, so it certainly can't be 9. So what we need to do is re-express this so that we take as many 4s out of that guy as we can. I'm just going to show you a little scrap work here. Think of this as 8 plus 1. 1 is going to be the remainder. So what we have here really is 16q squared plus 24q plus 8. Group that stuff together. And sorry, let me get that out of there so we can get the space. Plus 1. All right. And now the part in parentheses, you can factor a 4 out of each piece of that. So it's 4 times an integer. That'll be 6q and a 2 on the end after we pull the 4 out, plus 1. Now, since this 4q squared plus 6q plus 2 is a sum of products of integers, it's an integer. So that thing's an integer, and what does that tell us by the quotient remainder theorem? X squared mod 4 is 1. So our first case, we got 0 mod 4. Our second case, we got 1 mod 4. Then we got 0 mod 4 in the third case, and now here in case 4, we've got 1 mod 4 again. Every single case gave one of the alternatives we were looking for, either 0 or 1 mod 4. So we just need a kind of a final sentence to wrap it up and mention to the reader, look, this statement was true in all 4 possible cases, and the cases are exhaustive. There's no other options. So we're done. I'll mention that if you're in more advanced work, you might not even put this final sentence in. The reader can figure that out for themselves, but I kind of like to cap things off like this myself. Since the statement was true in each of the 4 cases, and also the cases are exhaustive, which just is a way to say that there's no other possibilities. Your values mod 4 are one of those 4 numbers we talked about, 0, 1, 2, or 3. So cases are exhaustive. That means we've proved the result by the technique of proof by cases. That was a little bit weird. I accidentally put this extra space in between the E and the M. The theorem is true. QED. Okay, so yeah, there's one more proof I want to do with you guys today, and that should be a wrap for Wednesday for my Monday, Wednesday, Friday class. For the Wednesday class, there's going to be a little bit of additional stuff in another lecture that I'll put in the can very shortly. But we've got one more result to do. I guess I'll spare you the deal of watching me erase. Okay, so what is this one last result I want to look at? We've looked at an example of using the mod operation. We've looked at an example of using the divisibility symbol. I wanted to do something also with the floor or the ceiling function. I think I'll use the floor. A proof for the ceiling would be very, very similar. So here's the statement I want to prove. For all x in the real numbers, and for all, let's call it n in the integers, the floor of the sum of those two things is equal to, this is actually very similar to a proof I had you guys try to do yourselves on the last worksheet. Take the floor of x, but n is an integer, so you just basically, all the rounding down that's going to happen is coming from whatever's in the after the decimal point in x. In other words, you can just add n on right there. Now, I think intuitively that makes sense, but coming up with a way to argue that it's true, that's a little tougher. I keep forgetting to label my theorems. Sorry. It's a theorem. Let's do the proof. This time I'm going to skip giving any examples to prove that it's right. So what's our first sentence? Again, this is just a plain direct proof, no cases or anything. Suppose x is a particular but arbitrary real number and n is a particular but arbitrary integer. Gosh, I don't want to have to say that particular but arbitrary stuff so much, and frankly, I think we're getting to the point where we can skip over that bit. Suppose we just say x is in the reals and n is in the integers, right? And you understand that, I mean, we're doing the method of the generalizing for the generic particular, so x and n really are particular, but no special treatment for them. They're just randomly chosen, so long as they live in the sets we're supposed to say. Suppose x is in R and n is in Z. This may be the most important word you use in mathematical proofs, the word let, because it's going to be useful for us to name the thing that's the floor of x. And this is how you introduce a new name for something. Since we were using x for the real number, I'm going to let y be the floor of that number. All right. I think it maybe even be that we used y in the definition on the definition sheet for the floor function. So if I say that y is the floor of x, what does that mean? I just mentioned the definition sheet, so we'll use that definition. Since, why did that come out white? Since y equals floor of x, by the definition, first off, y is going to be an integer, and secondly, that inequality that traps x between y and y plus 1. Right, y is, we were doing a floor, not a ceiling, so y is smaller than x. Y is on that end. X is in the middle, but y plus 1 is definitely larger than x, with a strict inequality there. Cool. Okay, so what are we after? We're trying to say something about the floor of x plus n. And if you think about the definition for floor, it has, well, here we were looking at the floor of x, it has x in the middle. If we were looking for the floor of x plus n, it would need to have x plus n in the middle. So it's actually not much of a leap to realize what we have to do to this multiple inequality in order to get an x plus n in the middle. and preserve its truth, we have to add n to all 3 bits. So y plus n is less than or equal to x plus n, which is less than y plus n plus 1. And that's just, simple algebra, so I don't have to really say much about that. I don't feel the need to justify it. If you guys want to, you could say by this property in algebra where you can add the same thing to all the parts of an inequality and its truth is preserved. So why is that good? This here is the definition of what it means for the floor of x plus n to be this number, the one on the left, y plus n. All right, so maybe I'll only do a half erasure job here because I think we can get to the end of the proof with only leaving the rest of it on the board. So, therefore, y plus n is equal to the floor of x plus n. Seems great, but in disguise, we're looking at the answer we wanted to get to. See, what was y? That was from our let sentence, let y equal the floor of x. So just undoing that substitution, the floor of x plus n is equal to the floor of x plus n. So adding the integer to x inside the braces is the same thing as adding the integer to x, to the floor of x outside the braces. You did. I think I had you on the last worksheet try to show that we couldn't do this, but it wasn't quite what I asked. In the worksheet, we were letting x and y both be real numbers. And this statement we just proved is not true if both of them are real numbers. It relied very heavily on y here being an integer, because otherwise this side wouldn't be a whole number, and so it wouldn't be the floor of anything. Okay. All right, well that's a wrap for the Monday, Wednesday, Friday class, and I'll talk more to the folks in the Monday, Wednesday section after this. So half of you I'll see you next week, and half of you I'll see you in a few minutes.